Hello and welcome back to this 24th lecture of BioMEMS, Bio-Microelectromechanical Systems. I would like to just have a brief review of the previous lecture. We talked about RNA transcription and translation processes. Transcription again is basically conversion of a double stranded DNA in the chromatin region of the nucleus into a messenger RNA. And translation again essentially is the change of language, that means from the RNA into proteins or a sequence of amino acids. And we saw how beautifully this nano machinery inside the living cell works, especially the ribosome, which kind of assembles all the different messenger RNAs and coordinates that with the transfer RNA, which is essentially around in the cytoplasm. And these transfer RNAs again have amino acyl groups which kind of conjugate with the messenger RNA on a base pair or a base triplet by base triplet basis, and thus there is a sequence of amino acid which is generated. So this is a very interesting process because this coding essentially is also responsible for the physiological state of health of a living cell. So we also described about antibodies and antigens, and would be doing this a little bit later in more details. And then we briefly talked about enzymes, where we were just about to begin what we know as the Michaelis Menten equations of the formulation of an enzyme substrate complex. So today we will actually focus a little more on these three areas and then try to go ahead and derive these set of equations and see what the enzyme catalysis rate would be in a typical chemical reaction. So to begin with, let us look at why all this is important really. I mean, we are talking about enzymes, we are talking about proteins, we are talking about antibodies. From a BioMEMS perspective, it is almost always essential that we have immobilization mechanisms wherein all these groups, all these different moieties are used for capture essentially of targets, okay, in the analytes. And for sensor design point of view, it is a very important aspect that these antigens, antibodies, etc., which are specific to capture of a certain reagent or certain analyte, is immobilized onto the surface of biochips or biosystems. So some of these immobilization mechanisms are, for example, antigens and antibodies, as you can see here. They are complicated folded structures, binding and their binding mechanisms are through hydrophobic interactions, hydrogen bonds, ionic and van der Waals interactions. Typically it is almost all antibodies are like these Y-shaped molecules, and they are proteins essentially with two heavy chains and one light chain. The light chain is at the base here, and these two are really the heavy chains of the antibodies. And what is also important to know is that there are these groups on the top here at both ends, which are also known as epitope sites. We will be doing this in just about next slide in a little bit detail. So the idea is that these sites correspond to certain constitution, certain molecular constitution, which can bind to flowing specimens like cells, bacterial cells, mammalian cells, different capture agents, so on and so forth. And so this is definitely one of the mechanisms of immobilization or capture of a certain specimen over a surface, assuming that you can somehow localize this antibody onto the surface of your choice along this lighter chain here at the bottom, and use these two as capture points or capture hooks, which can kind of collect flowing things in a medium. Then we also have these ligands and receptors. Essentially the very famous biological lock, as we popularly know this as, is called the Avidin biotin lock. So essentially these are two moieties. Avidin is essentially a protein and biotin is a vitamin, and there is a strong bondage between the two. They have a very high affinity constant of the order of about 10 to the power of 5, 10 to the power of 15, I'm sorry, mole inverse. And essentially whenever these two species are together, they almost always bind with each other. So assuming that you have a biotin end group or a biotin moiety put into one of these biological entities, like let's say an antibody or let's say a protein of a certain interest, then you can easily bind 2 such proteins by putting this avidin lock in between. So, you flow the biotinylated antibody in question, and then you put another avidin molecule in between, and then you have another biotinylated antibody. So, it can kind of form into a sandwich mechanism of 2 antibodies together. So, these molecular locks or these concepts of ligands and receptors can be very effectively used for immobilization of some of these biological moieties onto biochip surfaces. Okay, they are very commonly used in assays, and these have strong, especially the avidin biotin lock, it has strong affinity constant of the order of 10 to the power 15 mole inverse again. Another very interesting mechanism is how you can really attach these antibodies etc. to surfaces using the BSA avidin complex. So, this is very interesting, this is very important to describe as you can see here in this particular figure. So, essentially there is a silicon dioxide surface, okay, and this right here is essentially the surface, as you can see, this is the oxide surface, and what you do is you take this BSA molecule with a biotinylation done onto this molecule. So, BSA or bovine serum albumin is essentially a protein, okay, and there are certain protocols in which you could actually, by using the differential binding of moieties to each other under certain pH, bind a biotin moiety onto the surface of a BSA molecule, okay. So, you can actually pass it through a protocol where you keep on changing pHs etc., adsorb that physically onto a silica membrane, and then put this biotin end group under a certain pH so that it can protonate very near to this BSA. So, they have a kind of ionic attraction, and although there is not a covalent bond, but then there is a tendency of this biotin to bind to the BSA molecule. And then essentially, so you have a biotin here, as you can see in this end particularly, bound to the spring like BSA molecules, okay. So, these spring like molecules on the surface are essentially what is describing BSA or bovine serum albumin, and then you can use a similar mechanism to bind an antibody with a biotin end group. So, you take an antibody and you pass it through the same set of filters and use the variation in pH etc., so that there is a ionic attraction developed between the modified biotin moiety and the antibody, and so there is some kind of affinity between the two, and they kind of bind ionically, and so you have a biotinylated antibody. So, you have a biotinylated BSA molecule on one end, you have a biotinylated antibody on another end, and all you need to do is to simply put an avidin moiety inside here. As you can look at in this particular figure, this right here is really the avidin, the green area that you are seeing here is the avidin, and you have a biotinylated antibody on one end and another biotinylated BSA. Another very interesting factor to mention here is that if you can really change the pH where the BSA binds to the surface of the silica or SiO2, you could actually develop ionic attraction between the positively charged BSA, that means you have a kind of hydrogenated amine group NH3 plus, and the negatively charged oxidized surface SiO minus, and so therefore there is always an ionic attraction between the BSA's other end here and the surface. So, one end has been bound separately to a biotin using a pH based mechanism, and then the whole moiety is brought close to this surface, and again a pH based mechanism is done in order for the BSA, which is biotinylated, to bind onto the surface using a similar chemistry or similar mechanism, and you are putting an avidin in between and then a biotinylated antibody. So, this essentially this whole structure is nothing but a molecular hook, okay, where what you get is the biotinylated molecule. It could be an antibody, it could be a DNA, it could be a protein, and so therefore this is a very good mechanism of binding. So essentially it is like kind of a covalent linkage which is developed through this BSA, avidin, biotin etc., where you can trap or hook molecules to oxide surfaces. So, having said this, let us really look into some of the binding characteristics, and especially this again holds true for enzymes. okay. And definitionally really enzymes are large complex macromolecules consisting largely of proteins and one prosthetic group which may be a protein or maybe some kind of a non amino acid organic or inorganic group, and the enzymes play a very vital role by behaving like catalysts essentially to move forward a reaction. So we will try to investigate the reaction kinetics in such a case, and we can kind of extend that to even the antibody antigen binding or the in solution or over a surface pretty much in a similar manner. So let us look at some of these basic kinetic characteristics and equations, okay. So if you look at the basic enzyme catalysis process really mechanism really, what it follows is the following. So you have a substrate here, mind you substrate essentially again is the molecule or the moiety in which we are trying to bind something or convert into some other moiety, okay. So here substrate does not really mean the physical meaning of it like a wafer. Substrate essentially means something to which the particular biological moiety, be it an antibody or an enzyme, would bind, okay. So you have an enzyme E which is binding to a substrate S here, and there is essentially an equilibrium established between these two. There is an intermediate complex which is formulated as you can see here, ES, enzyme substrate complex, which is essentially ephemeral in nature. It lasts very short and breaks down into an enzyme itself and the product. So an enzyme really comes out as it is, and so therefore it is just a catalyst. It does not, although it participates physically into the reaction, it is not a part of the product and it can retrieve itself back normally. So you have substrate and enzyme on one side, you are actually doing the reaction here at a certain equilibrium state where maybe the forward reaction has a rate constant K1, the reverse reaction has a rate constant K minus 1, let us say. It converts into an enzyme substrate complex and it again breaks down into the enzyme and the product at a forward reaction rate, let us say K2, okay. So in this kind of a situation let us actually see an example what kind of enzyme can do what kind of behavior to certain molecules. So we have many times before discussed about this famous glucose detection reaction. So glucose here is oxidized in the presence of this enzyme GOD, glucose oxidase, in order to convert again into an enzyme substrate complex, and then essentially the GOD separates out and you have gluconic acid and H2O which gets generated. So this is an enzymatic reaction, okay. Similar kind of reaction chemistry can as well be used for antibody antigen kinetics. It is very important to keep a kind of rate kinetics based method to ascertain whether what kind of times do we need to hold these solutions on a certain substrate or maybe on a certain wafer for the moieties to bind to that wafer, or indirectly if you want to perform a sandwich between two molecules in a solution, what kind of time delays should you do between different steps of the chemical processes for the binding to occur. So you have to have a good mathematical idea about the rate constants, etc. And so the enzyme, the model that we have taken here for describing that is really the enzyme substrate reaction, okay. So if we apply steady state approximation to this particular reaction system, let us say this enzyme plus the substrate getting into enzyme substrate and then again getting into enzyme and the product, okay. And this really is borrowed from the kinetic theory. So under this approximation it is assumed that during most of the time of the reaction the concentration of the enzyme substrate complex is steady. That means you have a constant concentration of the enzyme substrate complex as you can see here, and the rate of formation of the complex from its components is balanced by the rate of its breakdown back to enzyme and forward to its products, okay. So essentially there is some kind of a equilibrium between the enzyme substrate complex and enzyme product. Let us say we have the rate of formulation of the substrate dES by dt given by this particular equation, okay. So you have an enzyme E reacting with a substrate and the forward rate is K1, reverse rate is K minus 1 and it is formulating ES. Again you have another combination where the forward rate is K2 let us say, and you are converting into enzyme and product, Okay. So, here if you really look at the way it is formulated, or the amount of the substrate consumed is K1 times of concentration of S times of concentration of E from first order kinetics. Okay. And the amount of the reverse reaction, that means the breakdown of enzyme substrate complex into the enzyme and substrate, is at the rate of K minus 1 times of concentration of enzyme substrate. The rate of formation or rate of breakdown of this complex in the forward direction is really K2 times of the concentration of the enzyme substrate complex. So, therefore, because K2 is the forward rate reaction in which the enzyme substrate complex is broken down into enzyme and product, as it can be seen here. So, that is really the overall formation breakdown rate of the enzyme substrate complex. So, therefore, the rate of formation of ES enzyme substrate complex is given by K1 concentration S concentration E minus K minus 1 concentration ES, and the rate of breakdown of ES is K2 concentration ES. Now, these K1 K2s, K1 and K2 are the forward rates, K minus 1 is the reverse rate. Okay. So, assuming this to happen, we can say that if there is a steady state behavior of this reaction, and the way that the enzyme substrate is formulated, or enzyme substrate complex is formulated, is same as the rate at which the enzyme products are formulated, and the rate, and it's same as the rate at which the enzyme and substrate independently are consumed, then basically we can equate these two rates, and then say that the rate of formation of the complex is same as rate of degradation of the complex or deformation of the complex. And if we take that into picture, then we can say K1 times of concentration S concentration E minus K minus 1 times of concentration ES really is equal to K2 times of concentration ES. Okay. And therefore, basically the different rates all put together, K minus 1 ES minus of K2 ES is 0. Let us call this equation 1 at this time. So, we describe the enzyme concentration really in terms of the total concentration E0 of the enzyme as the concentration available free with the substrate and the concentration available in the complex state with the substrate. So, essentially if you do that, then we can write very safely that E0 the total enzyme available at any given point of time can really be represented as the concentration of E and concentration of ES. Okay. You see here in the reaction really, let us say you have the reaction written here as enzyme plus substrate giving enzyme substrate complex, further giving enzyme plus product. You can see here that the enzyme at certain point is really the sum of enzyme substrate and enzyme. Okay. So, assuming that to happen here in the whole reaction system, and if we substitute this, we call this equation 2, we substitute this 2 back in 1, we are left with the equation as K1 S times of E0, okay, where E0 is the total enzyme concentration at any given point of time, minus K1 times of S times of ES minus K minus 1 ES minus K2 ES, okay, is 0. So, this is by just substitution of E0 value, which is equal to the concentration of ES plus concentration of E at certain point of time in a reaction, okay, the equation 2. So, assuming this to be true, so we are able to solve from this really the concentration of the enzyme substrate complex at any point of time, which is equal to K1 times of concentration of S times of concentration of E0, the total enzymes available, times of K minus 1 plus K2 in brackets plus K1 concentration of S. So if we divide by K1 on the numerator and denominator, we are really left with enzyme substrate concentration as S times of E0, where S is the concentration of substrate, E0 is the total enzyme concentration, and this term here K minus 1 plus K2 by K1, okay, plus the concentration of S. Well, this is really known as the Michaelis constant, okay, upon the name of its inventor essentially, and the set of equations are called the Michaelis-Menten equations. So let us call it Km, Michaelis constant. So in this particular case then we can represent the Es value as really concentration S, concentration E0 divided by the Michaelis constant Km plus concentration of S. Let us call this equation 3, alright. So then really the overall reaction rate or rate velocity, rate of formation of products, any of them is given by the equation velocity V is equal to d times of product formulation the dP by dt, that means the rate of formulation of product, or the rate of formulation or rate of degradation of the substrate minus ds by dt, and given by the Michaelis-Menten equation as K2 times E0 times of S divided by a Michaelis constant Km plus S, okay, because essentially this is nothing but K2 times of the concentration of Es, which was derived from equation 3 before, alright. So therefore the reaction velocity V here really can be represented by K2 times of E0, the total enzyme concentration times of concentration of substrate S divided by Michaelis constant plus the concentration of the substrate. So there are several conditions here that this reaction or this equation can be imposed in. This is, let us call it 4. So in condition 1, let us suppose that this Michaelis constant Km somehow is very small in comparison to S, okay. So let us assume that in condition 1, just give me a minute here. So you have the first condition here called condition 1, where we assume the Michaelis constant Km to be very less than S. So equation 4 really changes into V equals minus ds by dt equals formulation of product dP by dt as K2 E0, because essentially Km plus S can be approximated as S itself, okay. So therefore it is really a case where the velocity of the reaction V is proportional to the concentration of the total enzyme E0 that had been given at the very beginning of start of the reaction, when the enzyme substrate was the complex was just about to get formulated. So therefore this is also known as the maximum concentration or maximum velocity V max, okay. So we call this the maximum rate of the reaction or V max, and one of the reasons why that is so is that if suppose there is some addition to Km, the value of V is always going to go down, okay. So therefore mathematically also this can be represented as the V max or the maximum rate constant or rate velocity or rate of formation of the product. Let us assume another case a little bit different, where the concentration of S is same as the Michaelis constant, and if I'll show you later in a plot how these different points are very significant for understanding the enzyme substrate formulation reaction. So let us say that in condition 2 here we assume that this Michaelis constant Km is approximately equal to the substrate concentration S, okay. So in this particular case what would happen is that you have 1 by V from this equation 4 can also be written down as Km divided by K2 concentration E0 concentration S plus 1 by K2 concentration E0, which is nothing but V max, as we just saw a little bit before. Okay. So, we are left with an equation of the form concentration of S equal to I am sorry 1 by V equal to Km divided by K2 enzyme concentration of the total enzyme time concentration of substrate plus 1 by V max, okay, where V max is, as you know already K2 times of concentration of total enzyme E0. This here right here, if you assume Km and S to be equal, can be represented as again 1 by V max plus 1 by V max. Okay. So, if Km is same as S here, if you substitute this, the concentration of S really goes off and you have 1 by K2 E0, which is nothing but 1 by V max. So, in this case really when the concentration of S is equal to the Michaelis constant Km, V becomes V max by 2. That means it is the half rate velocity of a particular enzyme substrate formulation, complex formulation reaction. So, let us plot now. I mean, if you look at really the curve here, the plot is between, let us say if you plot between 1 by V and 1 by S here, this is going to be a linear plot with a slope and an intercept. The slope is essentially V max. Okay. On the other hand, if you plot between the V max and the substrate concentration S, the way this plot would go is something like you have, let us say V max or V as on the y axis here, reaction velocity, and substrate concentration S in the x axis. So, in this particular case as we can see that as Km is very smaller than S and the V really approaches V max. So, let us say if we have a straight line here describing what we know as V max, then the reaction rate really should be asymptotically approaching this V max line, and this is what the relationship between V and S would really look like. So, a plot of V max by 2 on this particular equation would correspond to a point on the substrate concentration axis which would be equal to the Michaelis constant Km. So, this is essentially an experimental method of determining from reaction chemistry what the Michaelis constant Km would really mean at a certain substrate concentration. So, if you know what V max is based on your initial enzyme concentration, which is known, mind you, in a particular reaction this is really known, okay, and K2 is of course the forward rate at which the enzyme substrate is broken down into the enzyme and product. So, it is the product formulation rate. K2 is again the product formulation rate. So, if you know these two which would give you an indication of V max, then you could really find out what the Michaelis constant Km is by looking at the substrate concentration where at a point of intercept on the curve corresponding to V max by 2. So, this is really how the rate kinetics of the enzyme substrate reactions happen, and as a matter of fact any antibody antigen reaction also are kind of governed by the same set of equations. Only thing is that in this case probably the reaction kinetics is not bound by the formulation of an intermediate state. It is just a product formulating from a substrate and the participation of antibody is there on both ends of the reaction. So, let us look at a little more details of what really the antibody is or what their structures are in order to understand more. So, number one, the very important fact is that an antibody can be developed against any substrate any substance popularly known as antigen and it can be raised essentially. And so the idea is that the antibody developed would be highly selective to the substrate. Okay. So essentially the antibody can be developed against any substrate and can be made a very highly selective material to a particular substrate. You can raise antibodies within an organism. The idea is that antibodies, as we know, are proteins formulated by so called B cells within a certain living organism, and essentially the organisms can be used to develop antibodies which can be later on used for the purpose of capture or specific recognition in vitro. So therefore organisms develop antibodies which are proteins, and they can bind with an invading antigen and remove it from harm as follows. So the antigen and antibody binds together to form this particular complex, and the affinity constant in this particular case is actually the formulation of or the concentration of complex divided by concentration of independent antigen antibody, and usually it is very high, not as high as the avidin biotin link, but again K is usually about 10 to the power of 6 mole inverse in case of antigen antibody binding, which is a pretty high affinity constant. So if you really look at antibodies, they are Y shaped mechanisms like you can see here. So you have these sections here at the stem of the Y which are really light chains, okay, and the two upper sections here which are the heavy chains, okay, and essentially the overall structure of the antibody by and large remains constant. There is no much variation except the fact that there are certain subtypes based on what these chains are really. In mammalian cells or in mammalian organisms typically there are about 5 different kind of such subunits which can be categorized as this heavy chain, light chain structures or antibodies. What is interesting though is that the portion here on an antibody which is actually known as an epitope site is the only variation in the whole antibody. By and large the other subtypes of the antibodies which are available are only 5 in number, but if you look at the amount or the amount of variation that these particular sites would have or the epitope sites would have, they can be different, million different antibodies of corresponding to binding or which can be capable of binding to million different biological entities. So essentially this keeps on changing, the epitope site keeps on changing, whereas the other part of the Y, that means these light chains and these heavy chains, by and large remain similar except categorization into a few subtypes. So the different subtypes are also known as isotypes. Isotypes are essentially based on which heavy chain the antibody would possess. So as I indicated before, there are about 5 different antibody isotypes known in mammals so far. That is all the range that the antibody could have, except the fact that the epitopes are varied and numerous in region. Okay. So an antibody essentially made up of this epitope with the heavy and light chain isotype can bind to different targets, and the targets that they typically bind to are known as antigens. Also there is a huge diversity of the antibodies which allows the immune system to recognize an equally wide diversity of the antigenic systems. So the unique part of antigen is recognized by an antibody called an epitope, as I have indicated earlier and shown in the particular figure. So there are several advantages and disadvantages of using antibodies. One of the most prominent advantages are the selectiveness or the selectivity that these antibodies would normally possess between the different strains. Another very important advantage is that these antibodies are ultra sensitive, okay, to any kind of small variation in the analyte of interest. I mean the binding or unbinding is typically dependent on what is the characteristic of the particular analyte. If there is a slight variation, and also if there is a slight variation in the ambient, it can change the way that the antibody would form a complex with the antigen or bind with the antigen. Although when they bind, they do bind very powerfully, and that bond cannot be easily broken up. The only disadvantage is that there is no catalytic effect in this particular binding between antigen and antibody, as happens in the case of enzyme. So here whatever is bound, I mean it cannot be reconverted back into a proper, I mean a pure antibody again or a pure antigen again. It is a irreversible reaction of formation of the antibody antigen complex. So by and large these are some of the advantages and disadvantages of antibody antigen systems. Let us now turn into a little bit different component, how we can immobilize the different biological components. We have done a little bit of this while looking at sensors, but essentially as is obvious, the next question which comes into being is, after we have kind of understood the reaction kinetics and also tried to find out more details of the structure of these different biological moieties, how do we really use them in sensors, and therefore immobilization protocols are very important for that. So there are various methods for immobilizing. Can be absorption, it can be microencapsulated, can be entrapped on a particular electrode or a substrate. You can cross-link or covalently bond a certain biological moiety or entity. Okay. So really the lifetime of a biosensor is greatly enhanced by a proper immobilization technique. If you can choose the right immobilization technique, you can use the biosensors many times reusably without really very many changes onto the sensor surface. So based on the adsorption method that or based on the particular immobilization method from this different range of methods that I have stated before just about a minute back, absorption, microencapsulation, entrapment, cross-linking or covalent bonding, the typical lifetimes of a biosensors also vary a lot. Like for example, in case of adsorption, this is only about a day or so. Adsorbed substances really do not stay very long onto a surface, and they are kind of prone to deabsorbing based on change in the partial pressure of the atmosphere in which such a surface would be kept. The membrane entrapment that we have talked about here is typically about 1 week lifetime. It is pretty stable because membranes are essentially thin perforated structures which would be able to hold these biological moieties very close to a particular substrate. For physical entrapment cases, it is about 3 to 4 weeks. The device lifetime is greatly entrapped because of enhanced because of the schematic wherein this entrapment is in a gel kind of a network. And for covalent entrapment, again it is very high because there is a covalent bond now between the particular moiety. It is about 4 to 14 months. Details of the different immobilization aspects and schemes. The first aspect which comes into picture is adsorption. What really adsorption is really, I mean it's kind of some kind of either physical or chemical attachment over a surface. By physical attachment over a surface, what we mean is that, you know, if there is a size based selection of a certain moiety on a surface, that could be said as physically adsorbed onto the surface. Chemical adsorption on the other hand could be because of very many reasons. One could be just ionic attraction between the moiety and the surface. They are ionically opposite in nature, and there is a ionic bond which is formulated between the two. Or due to van der Waals forces, there may be the tendency of a particular chemical to adsorb onto the surface. It is the weak interactions between the moiety and the surface. So many substances really adsorb enzymes particularly on their surfaces. Some of the examples could be alumina, charcoal, clay, cellulose, kaolin, silica gels, glass, collagen, etc. One of the reasons why if you look at really the microstructural aspect of these surfaces, they are all very highly porous in nature, and essentially more surface area is involved. So therefore if the area is more, there is a tendency of the adsorption of a particular moiety to be more. So adsorption is a dependent phenomena on typically the number of binding sites that a surface has to offer. If you have more surface area, more binding sites, you have more adsorption. So some of the advantages of this process are that typically no reagent is required. Okay, that is the biggest advantage that adsorption has to provide, that there is absolutely no reagent required. and also there is no cleanup step, and there is less disruption to something like a biological moiety, an enzyme or an antibody, just because as less as possible, the involvement of chemical steps are as less as possible essentially. So adsorption can be classified into physisorption and chemisorption. This is physical adsorption, this is chemical adsorption, and people have been really studying this adsorption on a very modular manner. As I have already indicated, physisorption typically is caused by van der Waals bonds, which are usually weak, and occasionally hydrophobic interactions or a charge transfer process or hydrogen bonding. Okay, that is how physisorption would typically occur. Chemisorption on the other hand would be usually by the formation of covalent bonds, and it's a much more usually much stronger process of adsorption onto the surface. So the adsorption phenomena can be modeled, as you can see here, by the Langmuir adsorption isotherm. What this equation really relates is that relates the coverage of adsorption to the molecules on a solid surface to gas pressure or concentration of a medium above the solid surface at a fixed temperature. Okay. So essentially is also known as the Langmuir adsorption equation. Okay. So what is important for an adsorption process? One is the amount of active bonding sites or binding sites, which is also a function of the active available surface area of a particular moiety. That's very critical. Another is especially in gas phase absorption, the vapor pressure which is over the surface is very critical to determine what is the adsorption. If the pressure is a little higher, then the adsorption rate automatically increases, because you can think about it as some kind of a forcing mechanism for the molecules to seep through the different vias and trenches on a particular surface, and so therefore if the partial pressure is high in the atmosphere, the PA is high, then the adsorption rate is automatically increased. So adsorption is typically given or described by this equation here. Let us say S dash is the number of sites which are available on a particular surface. You are adsorbing particles pre onto these S dash or S star sites onto that surface, and the filled particle sites are represented as SP. So typically there is an equilibrium between these two. So you have S star, which is the number of active available sites, and P, number of particles, and then this is the filled site or number of sites which are fully filled, SP. So there is an equilibrium between these, as you can see. So the equilibrium constant here is really directly proportional to the concentration of SP, and it is inversely proportional to the concentration of the active available sites and the concentration of the particle P. Let us call this K. Okay. So equilibrium constant here is the concentration of SP by concentration of S star and P. So let us assume that the fraction of filled surface sites is equal to theta. The fraction of unfilled sites at a particular point instant of time is 1 minus theta. So you assume that you have a total number of let us say the total number of sites as n, and the fraction of those sites is theta, means theta n are the number of filled sites and 1 minus theta n are the number of unfilled sites. So Langmuir, what he did is he kind of tried to experimentally observe that how the rate of adsorption would be behaving if theta is increased, the fraction of the active sites or fraction of the filled surface sites are increased with time, and he found out that there is a relationship between theta. So if theta is decreased and the number of active sites are increased, the adsorption rate would increase. It is a directly proportional relationship. Also what he found out is if the partial pressure is high, the rate of adsorption would increase. So if you put this all together in an equation, you are left with rate of adsorption equal to Ka, is the adsorption constant, times Pa, partial vapor pressure, times n of 1 minus theta. So this essentially is the number of active sites which are available. 1 minus theta, mind you, is the fraction of the sites which are available for binding, or they are still not used up, and n is the total number of sites which are available. So n times of 1 minus theta is really the number of sites which are available onto a certain surface for the binding to happen or the adsorption to take place. So the rate is proportional to the partial pressure, as you can see, and also proportional to the number of active sites on the surface here. Similarly, the rate of desorption, the ability of a surface to lose a particular adsorbed species from it, is proportional to the number of filled sites that are on the surface. So if the number of filled sites are more, then the tendency of the material to get desorbed from the surface is also automatically increased, which makes sense and is more logical. Therefore, let us say the Kd is the reaction rate for the desorption, and the desorption really is independent of pressure. So whatever the partial pressure be, the desorption would appear to be, or would happen at a rate which is totally independent of that particular partial pressure. It is only a function of the number of sites which are filled or bound on a surface, and it goes up with the number of sites which are filled or bound. Okay. So Kd n theta is the rate of desorption. So at equilibrium, if we assume that these two rates of adsorption and desorption are equal, and then whatever is adsorbed after a while, after the steady state has been reached, would after all the active sites have been kind of filled up, would typically desorb of the surface or typically not bind, then we can calculate theta by equating these two. Let us say this is 1 and 2, they equate these two equations as k times of Pa by 1 minus k Pa, where k is the ratio between the adsorption constant and the desorption constant, k by Kd. Okay. And theta, the number of filled sites on a particular surface, is nothing but the ratio of the adsorption desorption constant times of the partial pressure of the particular medium divided by 1 plus k times of Pa. Okay. K is the ratio of the adsorption and desorption constant, as you can see here in this particular expression. So that is what would happen typically when in a gas phase adsorption process there is an equilibrium which is achieved or reached. And this gives you some idea of how you could study adsorption, especially physisorption on a particular surface. Let us look at a different technique now, the micro encapsulation, as I have been talking about before. So it is really the trapping of a moiety or a biological moiety in between two membranes, okay, or two membranous structures. So in this particular method, an inert membrane is prepared and it is used to trap the biomaterial of interest on the transducer surface, and essentially for the very first time this technique was developed for a glucose biosensor, and this was developed on an oxygen electrode. Okay. So it is essentially developed on an oxygen electrode originally for a glucose biosensor. So there are several advantages of the micro encapsulation process. Okay. One definite advantage, as can be illustrated here, is that there is a close attachment between the biomaterial and the transducer surface. You can think about this particular membrane set to hold together the biological entity very close to a certain surface, and therefore this kind of provides a firm binding mechanism of closeness of the entity to the particular sensor surface that is being used. So definitely it is much more closer as an attachment than, let us say, an adsorption, where it may just randomly adsorb on a surface without taking care of any textural issues of the particular surface. So there is also this process is also very adaptable, also very reliable. Okay. Because typically you do not have to modify the sensor surface. That is an advantage. You are trapping using an external membrane without any modification, chemical or physical whatsoever, on the sensor surface. The reliability of the biomaterial is maintained, particularly the enzyme or whatever you are immobilizing, because you are not chemically again reacting, you are keeping the biological entity in its original state as it is supposed to be. So therefore this results in a high degree of specificity almost always. Okay, because you cannot you are not modifying chemically the biomaterial that you want to place onto a surface. And also there is a good stability to changes in pH, because essentially since the biomaterial is in its own state, is it in its own nascent state, no chemical change whatsoever. Therefore, pH change would typically only induce very small changes to the parent molecule. Whatever those changes are would get registered, as opposed to a case where you would have modified the biomaterial already, so the changes would be much more drastic in nature. Okay. It also stabilizes the material against different ionic strengths of the solutions and different substrate concentrations. It can act as an inbuilt device to limit contamination and biodegradation, because again you are not handling, or you are not playing with the biomaterials chemical property in general, and it can be used to prevent infection, because you are trying to guard the biomaterial using a membrane and trying to guard it from getting in touch or getting contaminated with the patient's fluid samples which you are trying to measure with this. So you could always of course have an option of binding the biological molecules that conduct electrons such as polypyrrole etc. To make the membrane, so that you could actually have a electron transparent path from the biological moiety onto the sensor surface. So some of the membranes that are used in this kind of microencapsulation are cellulose acetate. Remember, dialysis membranes are made up of cellulose acetate, and they are put external to the body wherein the blood is flown, and there is always some kind of separation of essentially urea and other harmful salts in the blood. This which excludes proteins and stops the transportation of other interfering species. This particular cellulose acetate membrane is kind of, due to its hydrophobic nature, kind of prevents the proteins or some other interfering species to get filtered across it. Then you have other kind of structures like PTFE, polytetrafluoroethylene membranes. Nephyon is a very good material, polyurethane etc., which can be used successfully as for microencapsulating the biological moieties. The next in line is entrapment. That is another very important mechanism. Here you are really entrapping the material in a gel kind of matrix. So instead of binding it together within a membrane or between two membranes, you are now trying to bind it by entrapping it into a polymeric gel kind of matrix, okay, in this particular approach. And for that you first prepare a solution and then gelate it later under suitable conditions, after the enzyme or whatever biological moiety you are talking about is trapped within the gel matrix. And then finally a coating of this gel layer is provided over the transducer surface. So this process also has some limitations. One is that a large barrier is created. Essentially you have no control on the distance of the biological moiety from the sensor surface, as there is a thick gel which is entrapping the moiety in its thickness, and the thickness of the gel can be made thinner and thinner, but still there is no active control on where the entity is present. Is it towards the sensor surface, or is it away from the sensor surface onto the other surface of the gel? We do not have control on that aspect while preparing, and so therefore sometimes large barriers are created, and they can do all sort of things like inhibit diffusion of substrates. It can slow down the reaction in general, and therefore sometimes this is all at a cost of the response time of the sensor. It gets drastically changed because of fat or thick gel layers entrapping the enzymes. Also there is a loss sometimes of enzyme activity, because the gel surrounding is really not the natural surrounding of a certain enzyme, and therefore whatever chemical properties the gel has would definitely have an influence on the enzyme itself. So there is of course a loss in enzyme activity, particularly through the pores of the particular gel. So some typically used gels are polyacrylamide, starch, nylon, glutaraldehyde, and some other conducting polymers etc. Okay. The other technique which is important to be understood is cross-linking. This is an approach essentially where a biological moiety is kind kind of bound to a biosensor with a crosslinker molecule. So you have some kind of a ligand molecule which is on one side bonded to the biological entity and on another side bonded to the particular surface in question. Okay. So we call it a bifunctional agent, this kind of crosslinker molecule, and it's used for binding the biomaterial to solid supports. Okay. It has been of course proven to be very useful technique, particularly to stabilize the adsorbed enzymes, and of course this technique also has some limitations. Some of them is that it sometimes causes damage to the enzymes because you are playing around with the chemical nature of the enzyme itself. You are trying to modify the enzyme to kind of cross link it to the linker molecule or the ligand molecule. So it causes some damage to the normal functionality of the enzyme because its structure is changed, and proteins, as you know, are extremely sensitive to this change in conformation. Their whole properties change because of a slight change in the conformation of the molecule. Also one more interesting factor here is that the diffusion of the substrate is sometimes limited because cross linkers typically form a dense brush like material onto the surface of the sensor, which can inhibit the flow of the substrate material very close to the electrode, resulting in loss in information or loss in signal connection. And of course there is a very poor rigidity or mechanical strength because these are all just sometimes chemically cross-linked, and they are themselves not very strong as molecular bonds, and so therefore we have to largely depend and rely on the nature of the material. Okay. So some examples are typically the cross-links that are formulated to cysteine residues in proteins, etc. The other mechanism that I would like to talk about is really covalent bonding, wherein, as you can see here, some of these functional groups present within the biological moiety is directly bonded onto the surface, and essentially it can be covalently bonded to the support matrix to just be a part of the surface and do its job. So the method can use the presence of groups such as NH2, COOH, OH, C6H4OH, SH, etc. develop charge on it so that this charge could ionically bond or attract or do some kind of a direct covalent bonding with groups onto the substrate surface. Now these, for example, are some of the illustrations where it talks about how different moieties can be covalently bonded onto the substrate surface. So with this I would like to end this particular lecture, and we will cover some stuff related to things like cyclic voltammetry and some related to electrochemistry on an electrode surface in the next lecture. Okay, thank you.